So we're going to talk about using the molecular formula to get some structural information. And that is doing a process called degrees of unsaturation. It's a little calculation. When they say unsaturation, what they're talking about there is they're talking about pi bonds and rings. So if I have a molecule and it has one pi bond, that would have 1 degree of unsaturation. If I had a molecule and it had, let's say 2 pi bonds. Oops, there we go. Let's say it was something like this. That would have 2 degrees of unsaturation. Another thing that also has 2 degrees would be something with a triple bond, because that's 2 pi bonds, right? So that would also have 2 degrees of unsaturation. So it's pi bonds and rings. So another thing that could have 2 degrees could be a ring. The ring is 1 degree. And what if I put a double bond in it? That'd be my 2nd degree. So this would also be 2 degrees. A ring is 1, pi bond is 2. So it's basically any structural element that makes this thing not just an alkane, right? Not just a normal single bonds all the way through. So you could have a 1 degree of unsaturation. Let's say we bumped it up and you had an O in there. Something like that has 1 pi bond, 1 degree. So it's basically telling you how many multiple bonds, how many rings do you have. So that's just a really quick little calculation. And I just want to go through how to do it and kind of formalize the steps. And then we'll do some practice. So you guys have your formulas and you'll need to do this for your formulas. So to calculate the degrees of unsaturation, let's say the first example is that let's kind of formalize the steps and then we'll do examples. So the first thing that you do is you get your molecular formula. And then the second thing you do is you have to adjust it for any atoms other than carbon and hydrogen. And you'll see why in just a minute. So we're going to do an adjustment. If we have O's, we have to do an adjustment. N's, halogens, anything that's not carbon and hydrogen has to be adjusted. And then we're going to compare that new formula, your adjusted formula, to a fully saturated formula, to a fully saturated alkane formula. So an alkane that's fully saturated is CnH2n plus 2. So we're going to take our formula, adjust it down to just C's and H's, and compare it to if it was saturated. And then we're going to ask ourselves, how many hydrogens are missing? So you just look at the difference. It's a quick subtraction. And then the next step, we'll divide by 2. And that will equal to the degrees of unsaturation. So let's just do, before we launch into things, I want to talk about kind of the steps with a small example and talk about why the missing hydrogens is even important. And then why do you divide by 2, which seems kind of arbitrary. So before I launch into this, make sure you guys can all hear me.
Yes.
Yep,
Yeah.
perfect. Okay, so let's talk about kind of the magic part of this. Why do you care hydrogens and why divide by 2? And we'll do it with just looking at some molecules. If I have something fully saturated, like say butane, for example, it is C4H 2N plus 2, so 4 times 2 is 8, plus 2 is 10. So this is C4H10. And butane, let's just look at the middle carbons. There are 2 hydrogens on those middle carbons, right? C4H10. Now what I'm going to do is draw a molecule that has 1 degree of unsaturation. So it has a pi bond, say, in it. So we'll draw our new molecule right here. And I'm going to put a pi bond right there. Now, in order to accomplish that, to put that pi bond in, I had to remove 2 hydrogens to accommodate that. Otherwise, I'd violate the octet. So I still have a hydrogen up here, and I still have a hydrogen down there. But I removed this guy and this guy, right? They are not part of my formula anymore. And so this is C4H8 when I count it up. So if you form a pi bond or a ring, you have to remove hydrogens to do that, right? And for each one of those, you have to remove 2 hydrogens. So that's why I'm figuring out how many hydrogens are missing. And then I divide it by 2 because each 2 hydrogens missing, if I'm missing 2 hydrogens, that equals 1 pi bond or 1 ring. Now to see the ring, imagine just with your butane that I took, and this is CH3s now at the end, right? Imagine I just took and bring the ends together. There's a ring, right? Well, they can't be CH3s anymore. They have to now be CH2s. So I have to lose 2 hydrogens. So every 2 hydrogens missing is a ring or a double bond. So that's why I find out how many are missing, divide by 2, that gives me the number of rings or double bonds. So it's actually not some crazy magic. There's a logical reason to it. So we're going to go through this for 4 different functional groups and show you guys how to adjust your formula to make this work. So let's do first, and let's just go down to a whole new page. So our first one we'll do is if you're lucky and you have just carbons and hydrogens. So call that number 1. So your formula is carbons and hydrogens only. This is easy because there's no adjustment. You can just compare directly. So let's say, for example, that I had C7H16. No, that's boring. Let's do C7H10. So that's my formula. What you do is I don't have to account for anything that's oxygens, nitrogen, so I'm good to go. You just figure out if this were saturated, so there were no pi bonds and no rings, it's just a straight out, let's say heptane, for example, it would be C7H 2N plus 2, so 2 times 7 is 14, be 16, C7H16. That's what it'd be. Then you just subtract. C7H16 minus C7H10, which is mine. I am missing 6 hydrogens. Then I divide this by 2. My degrees of unsaturation is 3. So this tells me that I could have 3 pi bonds. Could be. I could have, so this would be like three alkenes. Okay, that's one variation. 3 alkenes. Probably unusual and not likely. I could have 1 alkyne, which is 2 degrees, right? That'd be 2 degrees of it, plus 1 alkene. That'd be 1 degree. Could have that. I could have 3 rings. Super unlikely. I could have 1 ring and 2 pi bonds, maybe. That's a whole bunch of possibilities. And so let's just draw one potential. What if I had a ring and it was, say, 6 carbons? Yeah, I guess that'll work. So that right there is 1 degree. Then let's put a methyl on for my 7th carbon. Now I've got 1 degree there. I need to add 2 pi bonds into this to make my other 2 for a total of 3. So I don't know, I could maybe put 1 there and 1 there. Could be that. Could be a 5-membered ring. That's 1 degree. What if I had a 5-membered ring and then 2 more carbons? So that's my 7 carbons. And instead of 2 double bonds, what if I did a triple? That's the 2 for a total of 3, right? So there's a bunch of options, but at least it tells you when you go to the IR, start looking for double bonds and triple bonds. You know that there's most likely something like that there. So it helps to narrow your focus a little bit. Let's have you guys practice one real fast. Try C8H10. Calculate the degrees there. See what you come up with. I'll walk through it in a minute with you. Okay, so first step, if it's saturated, it's C8H2N plus 2, 2 times 8, 16, 17, 18. C8H18. Then I just subtract. I have C8H18 minus C8H10, and I'm missing 8 hydrogens. Every 2 missing is a bond or a ring, so I divide by 2, and I get 4 degrees. Any questions on that? All right, now here's a huge hint. You want to definitely, if you have 4 degrees or greater, that would be like 4 double bonds, right? Unlikely. Or like 2 triple bonds. That's kind of weird, right? If you have 4 or greater, what is almost always like 99% of the time in your compound is this. You have a ring, a 6-membered ring. That's 1, right? You got 1 ring, that's 1. That leaves 3 to go. 3 double bonds. It's a benzene. If you have, a benzene is 4 degrees. So let's say you have 5 degrees. You've got a benzene plus something else. Okay, so anytime you have 4 degrees or greater, don't go banging out 4 double bonds in a row. Do a benzene ring. All right. Questions so far? You guys good? Okay. And I assume you can all hear me. I don't see any emails that no one can't, so I think we're good. Okay.
We can hear you.
Great. All right. So let's do some other formulas. Some of you guys have halogens. So if your formula has a halogen, we have to adjust it. And the adjustment is, it seems a little bit weird, but we're going to adjust for that halogen, and we're going to adjust it to just C's and H's only in the formula. But we have to do it in such a way that we don't like create unsaturation. Okay, so we have to see what a halogen does to the molecule and then figure out how to deal with it going back to just C's and H's. So we're going to make a fake formula, basically, that has the same level of double bonds or rings or whatever in it. So in order to see what in the world I'm talking about, let's do a quick little example. And we're going to do propane. So propane is a C with 3 H's going to a CH2 going to a C with 3 H's. And now I'm going to put bromine somewhere on it. Let's stick it, I don't know, in the middle. So I'm not going to change the bonding at all. It's going to be all single bonds still. So I have H3C going to C, now just 1 H. I'm going to put a bromine in the place of a hydrogen and going to a CH3. So the first one was 0 degrees of unsaturation. And the second one is 0 degrees, right? So you can see when you're keeping the unsaturation the same, but you add a halogen, that the bromine took the place of a hydrogen, right? So for my count, the bromine effectively is a hydrogen, right? It's just like a hydrogen, just for my counting purposes. So what you do when you have a halogen is you drop the halogen from the formula and you add 1 hydrogen to the count. So let's do an example. Let's say I have, as my example, C6H9Br. To adjust this, I'm going to drop the halogen. So I usually just draw a line through it. And it is just like a hydrogen. So if I drop it, I'd better add 1 hydrogen into my count. So my count is just like this was C6H10, right? Just in terms of structurally, if I was just going to have hydrogens in there instead of a halogen, it's like C6H10. Is everyone okay with what I did there? Okay, now let's go ahead and get the degrees of unsaturation. Once you've done that, the problem is very redundant. So if it were saturated, it would be C6H2N plus 2. 6 times 2 is 12, plus 2 is 14. Mine is C6H10. So I'm missing 4 H's divided by 2. 2 degrees. So, I don't know. Let's draw something. I'm gonna guess a 2 degrees, let's say 1 ring, 1 double bond. I don't know. That seems kind of reasonable. What if I did a 6-membered ring? That's 6 carbons. Put a bromine on there and put a double bond. That's one possibility. But if this was me, 2 degrees, I'd go to the IR, start looking for C double bond C, maybe a C triple bond C. That'd be another possibility. It could be something like this. Let's say it's a 6-membered ring, maybe a triple bond at the end and a bromine somewhere out here. That'd fit too. The IR will tell you immediately which one's right and wrong. If it's a couple doubles, a ring and a double, or a triple, you'll know. Okay, questions on halogens? Okay, now a lot of you guys are going to have hydrogens, or oxygens rather. So we are going to have to figure out how to adjust that to just C's and just H's. And to do it, let's go back over to our little propane. All single bonds. And what I'm going to do with my new formula is put an oxygen in there. I'll put it in the middle again. So it's all single bonds still. I don't want to alter the bonding. It all has to be single bond. So I'm just going to pop an O in there. Now, you have to build a stable molecule, right? So the oxygen took the place of a hydrogen. So it replaced a hydrogen. But what I have there is not stable. You just can't have an O sitting there, right? Normally we would, if we're doing like a Lewis structure, we'd make a double bond, right? But we have to, for this exercise, keep it at 0 degrees. So I can't make a double bond. So the only thing I can do to make this work out is put a hydrogen on there. It has to have a hydrogen on it to be all single bonds. So the oxygen replaced a hydrogen, but really it just transferred to the oxygen. It just moved. So it went from the carbon, which had 2, now the carbon has 1 and the oxygen has 1. So the net effect is oxygen has no effect on the hydrogen count. I still have the propane is C3H8, and with the oxygen, it's still C3H8, but now there's an O. So if you have oxygen, I always loved oxygen. What you do with oxygen is just simply ignore the oxygen and leave the hydrogen count alone. That's how you deal with oxygen. So let's do a real example. Let's say I had, C7. Let's do C8. Let's do C8H8O. See what happens with that. I think that'll work. So you guys work on that for a second and then we'll compare answers. Okay, according to the rule, I just ignore the oxygen. So this is like, for the purposes of this calculation, it's like C8H8. This thing was saturated, be C8H2N plus 2, 18. So minus C8H8. I'm missing 10 hydrogens, that's a lot. Whoops. So I'm 10 hydrogens short. I'll divide that by 2, 5 degrees. Now, it's 4 or more, remember, is a benzene. So I know that in this thing is a benzene plus something else. So let's go ahead and draw some possibilities. I got a benzene. That's 4 degrees. I need 1 more degree. So if I have 1 more degree needed, and I have an oxygen, my first thing that I'm going to think is a C double bond O. Probably have a ketone or something in there. So it could be, this is 6 carbons, 7, 8. It could be that. But I mean, it could, another reasonable thing might be, what if it's an aldehyde instead? Put the carbonyl at the end. Aldehydes and ketones look a little different. If there's no C double bond O in my NMR, or maybe it's this. Could it be like maybe a C double bond C? That's another 1 degree right there. And maybe an OH on the ring or something. Maybe it's an alcohol. You get the idea though. You start just drawing things that's a benzene, which is 4 degrees, plus some other double bond somewhere in some form. And I'd go and look at the IR, and all these would look different. And then I would start to know, oh, there's no OH. I know it's not that. I do see a C double bond O. Then you're starting to look at something like that. So it really helps to narrow your focus immediately, knowing this degrees of unsaturation. Questions so far? Okay, and just to double check, you all can hear me, correct?
Yes.
Okay, perfect. All right, let's go ahead and do the last one. Whoops. Hang on, guys. Are you still there? I turned my iPad off. Did I lose you?
We're still here.
Okay, good. I hit the wrong button. It popped loose out of its case, and putting it back in, I turned it off. Let's say some of you have a formula with a nitrogen. Nitrogens always are a little bit weird for people. It's not like their favorite thing in the universe. Okay, in order to see what's going to happen with a nitrogen, let's do the same thing we did. We'll build up the plan with propane and see how we adjust for a nitrogen.
You're not sharing your screen.
Oh, I'm not anymore. Okay, let me go fix that. Now, can you see it?
Yes.
Perfect. Am I still recording?
Yes, it looks like.
It looks like, okay, good. Okay, so we will do propane. It goes to a CH2 and goes to a CH3. Now what we're going to do is substitute that out. I'm going to move this a little lower. Substitute a nitrogen in there. And we'll go to the middle again, just like we did. So there's a nitrogen. So we have that nitrogen replaced a hydrogen. Now, I got to make a stable molecule. I cannot add double bonds to this. I have to just add hydrogens. So this nitrogen always has 3 bonds, right? So nitrogen replaced a hydrogen. And basically the hydrogen transferred from, and let's draw it in red, it was on the carbon, right? It was a CH2, so that hydrogen basically ended up right there. So that was a transfer, but it added an extra hydrogen. So if I look at my count, propane was C3H6H8, right? When I stuck this nitrogen on, it became C3H3678 C3H9N. So I can't just ignore the nitrogen, right? If I drop it out, I still have too many hydrogens because I added that extra one. So you have to drop it out and subtract a hydrogen. And that's the plan with nitrogen, is you ignore the nitrogen, but you have to subtract one hydrogen from the formula. So that's the adjustment. So let's go ahead and let's do an example with that. Let's do C5H9N. So according to our plan, we're going to drop the nitrogen and subtract a hydrogen. So this is just like C5H8. If it were saturated, it'd be C5H2N plus 2, so that'd be 12. We have C5H8, so we're short 4 hydrogens. Divide by 2, 2 degrees. So, I don't know, let's do a ring and a double bond. What if I did this? Maybe a 5-membered ring. Maybe there's an NH2 on it, so that's 5 carbons, 1 nitrogen, and I need a double bond somewhere, so maybe pop a double bond like that. Could be this. 1, 2, 3, 4, 5. What if it was a double bond to a nitrogen with 1 H? That's 1 degree, and a double bond there. Those would look different in the IR. In one case, I would have an NH2. The other case, just an NH, right? And see, then you start to go to the IR and you start to say, okay, do I have an NH2 or an NH? Do I have any double bonds? Do I maybe have a triple bond? You know, it could be that. What if it was 5 carbons? A triple bond, that's 2, and an NH2. So I'd start to look for a triple bond. It's a lot of possibilities, but your IR will definitely eliminate some right away. Okay? So as an example, sort of tying this all together in terms of what you're going to do, I have an example formula and an example IR, and we're going to combine all these ideas and figure out the structure, just like you're going to do with your unknowns. All right, so first thing you do, you've got your formula, get the degrees of unsaturation. So we have oxygens. Oxygen, if you look back, we ignore it and leave the H count alone. So I'm loving this, right? I just cross out the oxygens and I go, this is like C9H10. Okay, if it were saturated, it'd be C9H2N plus 2, 2 times 9 is 18, plus 2 is 20. Be like C9H20. But I have C9H10. I'm missing 10 hydrogens. Divide by 2. I know what's in this molecule. It's 5 degrees. What does there have to be?
Benzene.
There's benzene, absolutely. So, I mean, or it could be like some freakish molecule and it's full of triple bonds and double bonds. I'm pretty sure it's a benzene. So I am going to, before I go any further, go to my IR. Oh, it's pretty busy, right? Is there evidence of a benzene in there?
Yes. There's a wiggle
Yeah.
waggle.
Yeah, there's a wiggle waggle, potential wiggle waggle. I should have sp2CHs above 3, and I do. Probably those two, actually, is probably. So this is sp2CHs. I've got a wiggle waggle. I should have a C double bond C at 1600, and I do. It's pretty big. It's right there. So that peak is my C double bond C. I've got a benzene. What else do I have? Take a look at the formula if you're not sure. It was C9H10O2. I've got oxygens. What do you think also is probably in there?
C double bond O.
A C double bond O. Particularly when I see O2, my first thing I know I want to be sensitive to, since there's two oxygens, carboxylic acid or an ester. That was actually the first thing I noticed before I even did the degrees. I have two oxygens. I'm like, carboxylic acid or ester? Maybe, likely. But it could be that it's not. It could be like a ketone or an aldehyde and maybe an ether. Okay, that'd be a possibility too. But let's go see if there's a C double bond O. There is, right? This big thing right here. So we have a C double bond O. Okay, so now pay attention to the location of the C double bond O. This can tell you something. If it's at around 1735 to 1740, think ester. If it's around 1710-ish, carboxylic acid, ketone, aldehyde. If it's low, like 1680 or lower, think amide. Now, I know it's not an amide because I don't have any nitrogens in my compound, right? So I can safely say I'm not going to consider an amide. That would be unwise since I have no nitrogen. In terms of its position, let's draw a line straight down from it. It is at best, it's 1700. It looks to me like it's a little lower, like maybe 1690. Okay, definitely not 1735 to 1740. It is too high for an ester, or too low rather, sorry. It is too low for the ester. Okay, now something that confuses people, esters have 1735, 1740, and they have 1250 and 1050. And let's go down and look at a kind of a complication here. And I'm going to go to, let's go to orange. So let's say I decide that, okay, maybe it's an ester. I think it's way too low. But let's say I decide it might be. I look for 1050 and 1250, and I actually do see those peaks. There's a 1050 and 10, 11, 12. There's something that potentially could be a 1250. And I look at that and I'm like, oh, maybe it's an ester. But the carbonyl is too low. You have to have all three things together. And so even though it looks like, ooh, I've got the 1250, I've got the 1050, I don't have that key part. So it's very unlikely that it's an ester. It'd have to be freakishly conjugated for it to be that low. Okay, down in the fingerprint region, you can really get led astray down there. but you have to take all the pieces together to make a decision. Okay, so I'm thinking no on the ester. Okay, preliminarily, we may have to travel back to that, but I'm thinking no right now. So carboxylic acid, is it a carboxylic acid?
No.
I don't think so either. It hasn't got the big bleh like that, so I'm thinking no on that. Ketone or an aldehyde? A ketone's hard to tell. An aldehyde, what were some peaks due to an aldehyde? Do you remember? We had certainly a C double bond O. What else was there? There were two peaks, one at 2700 and one at 2800, and they were due to the aldehyde CH. So I would go and let's look in that region and see what there is. I've got one thing right here. Just draw a line straight down, and it's around 2800, and then this here, it's around 27. It shifted a little bit, but it's real close. There is that double peak thing. And let's go, yeah, let's go green on it. Right there, there and there are peaks that would indicate an aldehyde. The aldehyde CH. So I'm thinking having an aldehyde is a pretty reasonable thing. Okay. Now, so I've got a benzene, and I think I have an aldehyde. Now let's just put the aldehyde on the benzene, just like that. The reason I did that is because an aldehyde is normally 1710. Actually, even a little higher sometimes. This peak is at about 1690, so it's low, which means it's conjugated. So I want that carbonyl right on the benzene so that it becomes conjugated and lowers itself. Now, my next step is I would want to know how this benzene is substituted. So I come down to the region between 700, so this region right here, to about 850, which is right here. That region, right in this area, is going to tell you the substitution pattern. And I have a big peak right there in that region. And let's do it in blue. This huge peak right here is about 850, and that tells you it's para-substituted. So I know I have something coming out there. So I have left, I've used 7 carbons, and I've used 1 oxygen. That looks like a 10. Let's put quotes around it, 1 oxygen. I have 2 more carbons to go, because my formula is C9. Okay, so I have 2 carbons and an oxygen, no OH. I'm thinking ether maybe? What if I just did this? Like that. And ether shows a peak at 1050. Just a generic CO. And I do have a peak at 1050. So that's not completely crazy. So that's a possibility right there. Okay, it's not the only thing though. I could do this. What if I did like this? Aldehyde, and then I had a CH2, an O, and a CH3. That's another possibility. And I could use like boiling point or something to differentiate between them. But I can't tell from the IR which one's correct.